Start recording. Okie dokie. So last time we had this interesting thing where we stuck a rectangle and a circle together. That was a neat trick. I didn't realize you could do that. We're halfway through.
Oh yeah.
That's cool.
I think it was a happy accident. I don't think we did that on purpose. But.
No, I do like when those happy accidents occur. So we have this system here where we're generating what these axes are for the circle and the rectangle, and then we're drawing them. So if you remember, so just going through what we did last week, we take the corners of the rectangle and we find the axes for the circle by subtracting, the top left from the circle position. That gives us a vector between, each corner and the center of the circle, which we then normalize to turn it into like a normalized axis. There's a universe in which maybe we don't need to normalize that, depending on how we're doing things, but because we want everything to be in the same sort of geometric space, we need to normalize them. How to best explain that? Like if we projected onto the unnormalized vector, we wouldn't be able to do a thing on axis 1 and on axis 3 and compare the results and have them sort of make sense. So we wouldn't be able to choose, for example, the minimum separating distance between these two axes because they'd be at different scales. So that's why we normalize them. Anyway, and then we draw some arrows to represent our axes and some lines. And yeah, that's simple, start there and draw it to there. And this one's like send it way off to that side and send it way off to this side. This is a little bit weird actually, so why don't we go in and change this, because these axes are all coming off the circle and we're spitting it out 1,000 there, but we probably want to do this. We probably want to grab circle position and just go from there, and that way we've reduced the amount of stuff here, which will become kind of important later. And then we've got more or less the same thing.
Sorry, I'm
just watching what you're doing. Oh, go for it. Your keyboard is less clicky than mine, so.
Yeah, I didn't clean mine up to match yours last time. Alright, so
and so that basically causes this code to look a lot like this code. And then of course this is the rectangle. We just know what the axes are, and at some point we'll probably want to go through and flip our y-axis over so that our camera is doing this conversion. We're not scattering this negative sign throughout the code. But for the time being, seeing as we're on a bit of a roll, we'll keep that as is, but we might go and fix that before we do any physics, just because it's going to get really ugly if we have, gravity is negative, for example. No, if gravity is positive, that's going to get really strange. So that's where we were at. Now, what we want to do is, so we talked about this last time, this is what we want to do next, and that is we want to make this system so that we're not just saying, okay, we have a circle and a rectangle. We want this code, particularly this next bit of code, to work for any axes. So the most obvious thing to do here is to say, all right, let's grab these axes and stick them all together like that. Grab these lines and stick them all together like this. And say, all right, we got some serious similarities here. We can obviously see what is the same and what is different between all of this code, and that's why we wanted to change that to, you know, these are the things coming off the circle, these are the ones coming off the rectangle. So these are still lined up axis 1 through 6. So we now have to basically turn this into a bit of code that's going for each axis in axes. Although we may want to in fact be like for axis count, which is more likely for reasons that we'll get into. So this is where I'm going to basically hand it over to you. What I will say before that though is we're probably going to need to allocate memory for this. And so for the time being, just for the sake of exercise, you know, feel free to allocate heap memory in the draw call with, you know, like a new vector2 array or something. And we'll come back later once we've got it working and we'll solve that problem as well. So over to you.
Sure. Okay, so I'll make my axes fit. Actually, I don't need that. Just throw in axis 1, axis 2, axis 3, axis 4, axis 5, axis 6. Okay, and then yeah, that's not. Yeah, the .NET disease in me wants to make an interface for those positions, but I'm gonna resist that.
Well, you know, it would be so nice if you could make a method that, you know, did a yield return. It's like, give me this axis, and you just iterate through that, you know, iterator method. But, you know, if have you ever loaded up ILSpy and turned off the thing where it decompiles the iterator method and just gives you the straight code for it?
I have not.
Ah.
That's the state machine for the enumeration, or the,
yeah,
the iterator? Yeah, I've seen the code.
Yes,
but...
there's like a blog post on it or something.
Yeah.
I think old new thing. Who's that guy?
That's
Raymond Chen did a blog post, and he basically posted this. Here's what that construct transforms into. It's like, that makes a class that allocates all this memory, and you know, it's good, but it allocates memory.
Yeah.
And yeah, I can't even remember if I can actually do this. For the people watching on YouTube, it's like I enumerable vector2 get new vectors, and it's like you know, do some calculations and then yield return foo, and then you can be like yield return, and each time you iterate through the result you'll get a different foo. But we try and avoid that for memory reasons. So this is looking pretty good over here.
Yeah, the only thing is oh no, actually I already have indexes. So let's make it weird, but you know, just trying to think about the fact. Oh no, I already. Sorry, making this more complicated than it should be. It's just the only question is, when I've created allocating axis 5 and 6, I'm not detecting whether or not, like, I'm just using the unit vector. So it would be kind of gross to be like, well, if the axis is unit y or negative unit y or negative unit x, then it's just, then choose the rectangle position. So because I have to determine the position, and I have a circle and a rectangle to choose from.
So we have more. We have to insert more information into this problem, basically.
Yeah. So, well, yeah. I mean, I could make a struct for it, but that's why I thought, well, you know, I was like, why can't I just, you know, grab this fun bit and just make an interface for the.
Ugh. Ugh. No. No. Oh god no.
But yeah, I mean that's one. But you know, technically that's one way to not worry about what shape you're dealing with. But we're not there yet, anyway.
Well,
Yeah, I mean,
there's two things that I'll say about that. First of all, is eventually we're not going to need this code. This is just for the debug drawing. So the actual algorithm doesn't require you to know the source position of each axis. So this is kind of just drawing fluff. The other thing is, and sort of the reason that I went with this axis count thing, is that we could just make another array.
fine.
And this sort of array technique is this sort of array technique is pretty pretty useful if you're, for example, possibly this is a whiteboard situation. We'll finish coding this up and then we'll talk about why we might want to go with that.
All right, fine. This is at least. Uh-oh. What did I do?
I'm wondering the same thing. So why would you replace? There we go.
What did I do? Mistake, clearly. It's like it's there. Circle, circle, circle. Rectangle, rectangle. This seems right.
Sorry, unfortunately, I was catching up to you, and so I may have missed what was going on.
Oh, I just feel like mistake.
I mean,
because there's just less happening now. Like once if I comment that out, then I end up with less happening on the screen. Then
let's have a look.
Like that doesn't.
Oh boy, something has gone terribly, terribly wrong there.
Yeah. Just have to recheck what a position is. Oh, you found it?
I found it. My cursor's pointing to it. If you can see my cursor. Do you get my cursor across?
Oh, derp. Typo of typos.
Oh, there's quality typo there.
Oops. Yeah. Caps off. Doing the wrong thing here. Escape. Circle. Tab. Rectangle. There we go. Okay.
Nice.
Good enough.
Okay. So, I mean, that's particularly handy because now we have this thing where we're like, okay, we don't have to worry about lost my train of thought. We don't have to worry about the specific shapes. We just have this loop that does the separating axis thing, and we can now just talk about axes and and projections onto them. So we still have a little bit more work to do. Right. So now, see, I'm going off script here because you've brought up something interesting, and I now need to open up a browser and find a thing. Let's see if I can find it real quick, because I know we were talking about this particular bit of code, which is the open source version of most of the engine for River City Ransom, and we were talking about can we relate what we're doing to this particular bit of code. And
what are you looking for?
There's a bit of code in here. I am specifically looking for the I'm trying to do this from memory on the fly, because it actually is interesting. It is
the repository search method. If you know the name of the class, you'll find it easily.
That's if I knew the name of the class. There's actually a bunch of these things, and I think the specific one I'm looking for is in the drawing system. It's the sort of drawable. Where is the draw sorting?
Register sort is on draw context.
Draw context,
isn't it? Or yeah, I would check I'd search for draw context up at the top.
Okay. Let's see if we can find this. Well, there's it being used. Drawable objects.
It should be just a file called draw context. Yeah.
I wonder where it is. Yeah, no, it's a sort of draw list is what I'm after exactly. So.
Okay, well that's an actor, so you'll probably find it in common.
Common?
Well, actor is right there on the main route, on the main path, and then that's the main game object.
So this is just to explain to everyone on YouTube, everything's moved since I wrote it.
No, nothing is moved. Everything that was in RCRU engine will be living in the engine subfolder, and everything that was in Pixel 3D remains in its existing structure.
Don't worry.
You can edit this.
Oh, here we go.
Cut out the.
Here we go. It's in Pixel. Now that you say that, it's like okay, engine is a subfolder, and I have to actually go up a level to get Pixel 3D, and here it is. I'm just going to open a couple of these. So I wanted to point at a system that is using this, and I'm going to pick a good one. Sort of draw list is tempting. Depends how it got written. Where's the actual lists? Okay, so
you're using structs there. Yeah, okay.
So, I mean, I am using structs here. I mean, if we look at what we've just done, I mean, we're technically using structs there because we've got vector 2s, which are structs. So here's one example. Here's, registered items for drawing. Here's their bounds, here's their sorting info, and here's their drawing info. If I jump over to Tarjan's algorithm, we've got something similar here. Here's working storage. So we've got the index, we've got the stack end, vertex index, vertex low index. This one's, I'm going to say way more complicated because where's even the count? Does this have a count? Maybe not. This one's a lot hairier because it's doing tricky stuff. But so let's look at this simple case. And to get the count of what we've got in here, so we're using lists here rather than arrays because I just wanted something that would grow yet still have otherwise the same characteristics as lists. So what happens is, let's see, what do we have? Well, let's go with our example. We have
yeah, when I said struct, I meant like we would take the vector axis and the position and put them in an info like info struct is all I meant.
Yep.
Which just removes having two array allocations and replaces it with one. But that might just be organizational.
Well, so basically what I'm going to talk about here is why we would want to have these split out. And there, if you saw the comment on the code, it was something called SOA. Have you ever seen this concept? Sorry?
I have not. I have not.
Okay. So there's a really great talk by, I'm going to mess up the spelling of this, it's Mike Acton, I believe. And he talks about sort of this in more depth and why you'd want to do it. Basically, the way this works is when you stick this in memory, what you have essentially is you've got, here's an axis, here's an axis, here's an axis, here's an axis, and so on. And you've got here's a position, here's a position, here's a position, here's a position. I probably should have drawn these in different colors, like. Whereas if we had like a thing like info, and it was just axis position, in memory it would look like this, and then you'd have position, axis, and so what happens is when you have a loop, for example, which we're going to have later when we're just talking about axes and we're not trying to draw this thing with positions. When you have a loop that cares about one part of this and not the other, when the CPU goes to read this memory, and let's pretend like a cache line is much smaller than it actually is, it's going to read in, it's going to say, okay, I want this axis, and it's going to go to the cache and it's going to be like, okay, it's going to grab out, say, this much memory. It's actually going to grab 64 bytes is the size of a cache line. So I mean there's 4 vectors in there, so I'm not going to do the maths now. It might actually be this much. So it grabs out this. We're then wasting this axis and this axis because, on the next iteration we're going to do that, and the next iteration we're going to do that, and the next iteration we're going to do that. Whereas if we had packed them like this, that one memory access is going to pull in 4 instead of 2. So does that make sense so far?
Yeah, absolutely. I mean, though in the Pixel 3D you were using info type objects, like is that because you know in advance that you're only going to ever access them and you're going to need every bit of it every time?
Exactly. So this is the reason why we have bounds, sorting info, and drawing info.
Instead of like one silly sorted draw object which has all that stuff in it, because you factored it along the lines of along the cache lines themselves.
Basically when is memory going to be accessed? So let's go through this because this is quite interesting. So we have the sorting info. This is like, what information do we need to sort this thing? We need what animation it is, we need its position, we need whether or not it's facing left. What do we need to draw it? We need to know, what draw method to call and what tag to pass through to the drawing. And then we particularly need the bounds because that tells us, what's on screen and stuff. And you can already sort of imagine it's like, all right, some of these will be needed in more places than other. And in particular, if we've got a this bounds thing, if we've got a screen, if we've got a screen and we're going through like every single object, so we've got this big array of like bounds, and every one of those has like a bounds rectangle in it, And so it's like one's here, and 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 you know, there, and there, and I don't know, there, and there, and there. And we're gonna have to, because I didn't do any like spatial partitioning, so I didn't turn this into a tree or something. It's a straight array, which is going to be quite fast because it's so simple, and we have like only, I don't know, a couple of hundred objects per level at most. So this is going to be fast enough. And so what it does is, you know, when you read this, it's going to grab all of this into memory. It's going to be like, all right, that's 64 bytes or whatever. And it's going to be like, all right, reject that one. Yes, that one. Reject this one. Maybe we'll say that's outside. It's like, oh, this one's... Well, okay, so it gets one and rejects two. So then what it can do is then, right, let's go and get the drawing info, and that's a completely separate array. And it's like, okay, give me, you know, element 2, give me element 2 in this one. And it will load up this. And I think this struct is slightly larger, so, you know, the memory access is going to be like, it's going to get that page and it's going to grab that. And, it, you know, it wastes that, but it's grabbing this. Whereas if this was written the other way, if they were interleaved, basically, we'd be grabbing basically one element at a time, because, you know, we've got this and we've got the drawing info, which say is half a cache line. And we've got the sorting info, which is probably another half cache line or so, just guesstimating. I mean, I actually worked it out at the time, I think. And so what you'd be then doing is you'd be grabbing, you know, your orange and your green and your, let's say, purple at the same time. And then most of the time, because most of these are off screen, because, you know, the level's quite wide, every single memory access is going to be wasted, except, I mean, checking the bounds. It's like, yep, that was a waste, and then so on and so on. So this basically reduces the number of memory accesses. The reason that's important is, and I'm sure you've probably seen this before, and that is a sort of memory access hierarchy. So you've got the CPU, and you've got registers, and they're basically free. And then you've got L1 cache. That's three cycles. And that's like, what is it? I think it's 32 kilobytes. Of data cache on a typical processor, I think. It might be 64. I'd need to look it up. I look it up every time I need to actually know it. L2, this is going to be like, what is it typically like? I don't know, let's say 4 megabytes. And then you've got main memory, which is, you know, this is across some, you know, motherboard here, and then, you know, RAM is there. So it's got to run through there. So this is about, what is it? I'm trying to remember these things. I think this is like 20 cycles. And this is like 200. It's 200 cycles, I think.
But it's, I mean, you can at least see the just, you know, it's almost exponentially.
Exactly. I want to say these two are actually bigger, but I'd have to look it up. But suffice to say, this gap here is pretty big. So this is our like fast storage. So not only when we grab this buffer into, like, we're grabbing this data into a register to do the comparison, it's going to take us 3 cycles to grab each one of those out of L1. That's not too bad. And we're probably doing like 3 cycles of work just to do the comparison. It's this transfer here to get the data from L2 into L1 that really, really kills you. So basically we're running through these, and, you know, each of these might take like I don't know. Let's say they take 5 cycles each. We can fit 4 of them in, and that's great. That means we're basically we're using more data out of L2 than we can out of L1. Like we're pulling stuff from L1 faster than it slower than we need to, because we're taking 5 cycles and it takes 3 to access. So the CPU will overlap these things, so it's got like one, they're firing off like that. Hopefully that makes sense, like memory access, process, memory access, process.
Right.
And so we've grabbed, I'm just making up numbers here, because this is actually somewhat on the fly. We've grabbed out, we're pulling enough data from L1 to make it worth it. If we were in this case, suddenly, if we do, this is not particularly a smooth presentation.
That's okay.
Suffice to say, if we're wasting accesses here, each one of those wasted accesses takes 20 cycles, and we want to limit the number of wasted accesses. Sorry, yeah?
No, I just had a couple of clarifying questions. One was in the source code comment. It said sorted SOA, and like I think that means even though like the order in which you're going to access those helper object or info objects matters. What is SOA? Do you remember what SOA stands for? Just so that
yes.
I stop thinking service-oriented architecture, which is bad.
I mean, this should probably be a lowercase o. It doesn't say sorted; it says stored.
Right. Sorry, stored SOA.
So these are in fact not sorted as such. In fact, I want to go down because I think there's actually. This is maybe not the clearest layout of this thing. Like this is the useful info. I think there's actually more data. Maybe. Yeah, okay, so there's a couple of more lists that you can kind of tell if you look at the reset method. It's like there's those 3, but there's also forced draw order, deferred, inherit draw orders.
And these are you like creating optimized layouts for data for access, right?
Pretty much.
I mean,
some of those
caching little bits you need for.
Exactly. Some of those may be like slapped in last minute, which is why they're down here. But all the same. So, and then we come down here. Here's the sorting. So, edge bits. This is the okay. Okay, and then it gets a little more complicated because all of these lists are in parallel to this sorted order, and the structure of this is not ideal. But this actually tells us the sorting order of these lists. So it actually gets a little bit more complicated than this because it's actually the hierarchy is not so much that we check the bounds of every single thing, although we do something similar to that. There's actually a layer above this, and this is like sort order.
Okay. Oh, right, sure.
And that does exactly the same thing. It's like, all right, pull out, as much data as possible, or basically as much useful data as possible, as in as little data as possible, yet still solving the problem, so that we can grab all of these, and they're going to like point at different things.
I guess when I meant sort, I meant simply that whether there was a benefit of keeping those orange lines in your diagram contiguous, as in left to right, coordinate-wise, as opposed to having, because you had to keep searching for the other one. Maybe you were going to be able to make an optimization if you knew that past a certain point there wouldn't be any in that space. But like you said, I guess that's me forgetting that you like literally said that you weren't partitioning it in any way, but I thought maybe you could, like, the orange lines here, note it, that X one, that the on the right side is actually further in than the one that's before it, right?
Let,
So I'm just wondering if it mattered
yep.
if these would be in order or not.
Okay, so let me spin up another page because, yeah, I kind of wish I'd thought about this and read through this code in advance because, let's try and get a little more rigorous as to what it does. It is actually kind of complicated, but basically we send it off to a sorting algorithm and we get back a list of sorts. This is basically integer indexes. So the whole thing is like a whole bunch of parallel lists going this way with, one specific count. Hopefully that diagram makes sense. So we've got, we'll have our bounds. So these were orange there, and we've got our sort infos, and they were like that, and we've got our drawing infos, and they were like that. And you can see that they spread out a bit more because they're different sizes. And then we have our indices. These are, I think, 30. I'm pretty sure I considered making these 16-bit integers for this reason, but they're 32-bit integers, which is 4 bytes. 64 divided by 4 is 32. No, it's not. It's 16. So basically, when this thing goes to sort, it can pull in 16 of these at a time. So these are going to come up into that 64 KB of L1. And when we send this off to the sorting algorithm, all we're sending is this array for the output and the sort info, which I think I actually made. I think I made that green. We'll call it green for now. It's sending the sort info and that output array. So already when we send this stuff off to sort, we're not sending any of that data and we're not sending any of that data. So we're loading that data into memory at all. Then it does the sort and it fills out this. Now the reason these are not sorted in here and they're sorted in this array is actually to do with this same thing. We don't want to be rewriting the ordering of this whole shenanigan because it's not just this array that we send off to the sort algorithm, but it's every single piece of data. So instead, we just sort indexes into the data because these are much smaller and we can pack more of them into each cache line and into the cache. So does that make sense so far?
Yeah, it does. I think, yeah, keep going. I think I derailed you by accident, but
no, that's all right. So I mean, this one would be like, well, what's the first thing we draw? Oh, it's like there. Oh, it's the second thing we draw. Oh, it's there, and so on. So
right.
this is
the further down you go, the more targeted you're gonna, because you have the indexes at that point. You're not actually doing scans or seeks on the cache data. It's the higher level ones that are getting you to the point where you can grab the other ones in the same indexes that you found in the previous one, which is why they're all kind of like lined up.
Yeah,
right?
Exactly. And this is in fact, like what I was saying before, is sort of a vague, like hand wavy explanation of what it's doing. What it's actually doing is it's like, all right, for this particular bit of code, we need the indexes and we need like this thing. And then much later on, when possibly some of this stuff has been evicted from cache for like other bits of the game to use the fast memory, later on we're going to come and draw these things. So we're going to pull this one into cache, and what's going to end up happening is basically this whole thing is going to get pulled into cache. But that's fine because that is like 1/3 of the total information that we have. So we've tripled effectively, and roughly speaking, the number of objects we can deal with at like L1 cache speed before we start hitting L2 and slowing down by like an order of magnitude, as you said.
Right. And I know that when we talked about this, when we were working on mostly optimizing code that I wrote about, getting it to line up with this concept. This I still don't know what SOA stands for.
Sorry, I was like, and I didn't answer your question. SOA is struct of arrays. It's the opposite of AOS, which is obviously array of...
Right, and that's what most people work on in like basically any other software. But
this is what the language encourages, because it's like that's what you have to do this thing. You obviously saw that we had to do that a bit of a handstand to like, okay, here's our array, and here's our separate count, and and we're doing it over in the other code with actual arrays rather than lists.
Yeah, I think this is a subtle but important thing, because I think you're kind of setting object orientation on fire there, and most people come from that.
Exactly.
Objects aren't driving the bus anymore. It's just these layouts of data. But I wanted to ask, because when we were doing this work, I remember they used the term cache coherency, and cache coherency, like the word coherence to me is like sameness, right? So this thing over here is the same as this thing over here. So what is that? What does it mean here? I mean, so you have copies of data in these L1 register, L1, L2 cache. Is that just saying that they're all the same, or how does that apply to this, if it does?
It basically means the data that I want is like is what I've been describing. Basically, is this is cache coherency, and it's like the data that I want is next to each other in memory, and if I have a loop that's like for I equals 0, I is less than count, I plus plus, foo I equals, I don't know, foo I times foo I plus 1, and then stick a cheeky -1 in there. What this is going to do when this loop iterates is going to go, all right, give me I, and this is foo here. Give me I0, and so that's going to go, all right, well, I don't have this in a register yet. So I need to go off to memory to get it. And let's say that this is sitting in L2, for example. So what this is going to go is going to go and ask L1. L1, do you have this? And it's like, no. Okay. So it's going to go, all right, L2, do you have this? This is going to take 20 cycles.
Right.
Hopefully we've issued this as a whole bunch of stuff above us in the pipeline. In the name of this particular bit of the CPU is escaping me, but there's a pipeline of instructions that are still happening, so we're not wasting too much here on our first access. So we're like, all right, let's go off to L2. 20 cycles later, L2 comes back and says, all right, this is now available for you, and we've loaded this into L1. So it's like, all right, great, this can keep working. So it's like, okay, give me I1. So this is 0. We've done that. We're doing 1. It's like, oh, great. This only takes 3 cycles because it's in L1. Then we do 3, 4.
Yeah.
While we're doing this, the CPU is actually really clever, and it's like, I see you've accessed that, and then that, and then that, and then that. I'm going to go and prefetch this. So already we're like, and it's like, I can grab that as well.
So you're going to get in the CPU's way if you don't align your data to match that, because otherwise it's not going to be able to do this optimization for you if you're interleaving everything.
Exactly. And I mean, so say we were interleaved like this, we've slowed down by like a factor of 2. If we're pulling in this data that we're not using. But the CPU is probably still doing a prefetch for us. we might get that data in time. It may be okay. So we can make, what that means basically, we can make fairly big structs in here. Like, so if this is like a vector 2, it's like, that's fine. If this is like a vector 2 and a vector 2 we don't need, it's a little bit of a waste, but it's probably not too bad. But once we start getting into like, the array of structs, like the way that people normally program, like you can imagine if I'd written this code, where is it? Here. We've got one. This is okay. So this is 4 bytes. This is 12 bytes. This is probably 4 bytes because I didn't really worry about flags too much. Here's another 4 bytes. Here's another 4 bytes. The bounds, there's going to be 16 bytes each, and already we're way over, like we're 1 cache line per thingy. So basically, you imagine I took this and I like deleted those lines and it's like just jammed them together, and then smacked in whatever bounds is as well. Then this becomes a multicolored rainbow of like 1 cache miss per object accessed, whereas this is like we cache miss once and then we don't cache miss again until we start doing something else.
Yeah, so OOP is a total lie then.
Pretty much, like, and then this gets into interesting stuff like if you've John Blow's language, JAI. Have you like surely you've seen this at least?
I've read of it, but I haven't actually seen the syntax or.
It's still pretty much in flux, and I think he actually pulled this out because he said, "Oh, I've got a better way of doing this," and he hasn't said what the better way is yet. But he actually had a thing where it's like you can write a struct in like the traditional way. It's like struct, A, B, B, C, C, D, D. These things might be huge. And then you like tag it as, I forget what the syntax was. It was like SOA. And then when you make an array of these somewhere else in your code, it's like if this is like let's call this Q. So if I were to, and I'm not using John's syntax here, I'm just hand waving it. But if I make an array of Q, so if I'm like 128, that foo. If I make this, the compiler will automatically split these into different things and handle all of the indexing and stuff for you. And it'll kind of feel like you're doing, just a standard struct, but in fact, it's going to split it up and make these memory accesses nice for you. So there's ways it could be done that obviously it isn't being done in sort of all of the C-derived languages, which is basically all of them. So yes,
wow,
that's the little diversion into why we one reason we want to do this sort of almost habitually. There's sort of coming back to this code. There's sort of no real major reason. It's 6 items. It's 6 items that we just calculated. So then they're probably already in registers and probably not in memory. So we're not really even optimizing it here. But this pattern becomes so ingrained that this just becomes the easy thing to do. It's like, oh, I've got some axes that I need for one section of code, and I've got some positions that I need for only another section of code, so I'm just going to split them up. And this is quicker. We don't even need to make the struct because we just do that and we just say we have a count.
Right. Yeah. Okay.
So
although
yes,
that's funny though, because I'm sorry, we're probably ruining the goal of this practice or this session, but it's like
no, it's fine.
But I'm looking at it. I mean, it's an array of structs though, like. Those axes and those positions are structs. We have an array of structs.
Yes, so it is an array of structs. Just like this code is like an array, although like list is basically a growable
Well,
array.
internally it has array. Yeah.
But it's structs. But the reason we call it an array, sorry, a struct of arrays rather than an array of structs, is because if we did it the other way around, it would look like this. So we'd have struct something is going to be equal to access to position, and then we just go.
We'd have an array of the yeah.
Yeah, foo equals blah.
So it's a logical distinction. Like it's not, because because we're newing up the array and we haven't manipulated the data. It's a struct of arrays as opposed to actually formulating the struct yourself and then arraying that. That's the action that does the work.
So you can imagine like I've just slapped these onto the stack, but you can imagine that if you are coding this in a way where it's like we're going to reuse this a whole bunch, and in fact we may actually do this at some point, it would look like this. So all of a sudden
Struct of arrays.
We have a struct of arrays, which are technically a struct of arrays of structs, but I mean that's
rabbits all the way down.
That's neither here nor there. That's
a language. I mean, how else are you gonna declare layouts of data?
Yeah, and I mean, like we could take this further, like and sometimes it's actually useful to do this, like float axis x, float axis y, and these would be arrays, and we do it that way. And now, unless you start like really hand waving, it's like, whoa, the floating point number is like a struct of like a exponent and a mantissa and a bit sign bit. Now we actually legitimately have a struct of arrays. So you can blow these out like this, but that's when it there's in a certain sense the terminology is like basically. Struct of arrays is like cared about the data, didn't give a blah
something. Yeah. Right.
So, like colloquially speaking, it's like I'd made this in struct of array form. It's like I actually thought about what the data's doing and where it's coming into the CPU and stuff. And I made a decision whether this should be like a float separated out like that, or a vector 2, or some combination. But the overlying thing is like there's a whole bunch of arrays at the top level.
In any like business developer who's like making games at night, like they kind of already know this concept of like master detail, right? You get the header information from your piece of data and you don't get the whole thing. You go out and get it later if you need it. But this is like taking that kind of data oriented idea and like moving it to right down into like the exact where the real code is happening. So it's an interest. Like I don't think it's insurmountable, but yeah, I mean there's like a lot of rethinking going on there to make that habitual for sure.
It's a great habit to get into. Like it's the only reason that this game runs like as fast as it does. And I'm just going through here. We probably can find like instances of this is a classic one. I hate this. Like this is one of the this tag matching is inspired by Valve's dynamic dialogue system. This was so clever when I came up with this, and it didn't work very well. But if you look here, this is the classic example of the struct of arrays. Here's our struct, in this case class, of arrays, and we have the tags that we're looking up on and the values.
Right.
And this is so this is exactly what we've been talking about. This is the I think this is like an example is correct terminology. So if you were making a dictionary, and there's a few of these in the code. So like if you look through the River City code base, you'll find this sort of thing happening everywhere. because it's so important. And so, like, if you were making a dictionary the dumb way, you'd be like, here's my keys, spelling, keys, here's my values, and we'd just be like, boom, 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 boom. It's like, all right.
Also known as what the framework gives you out of the box.
Well, if you actually look at what the framework is doing, in fact,
well, it uses the enumerable keys collection. I know it's a virtual collection, but
is it? In fact, I might show you something in a second. Reference source Microsoft.com. Please load. Here we go. Okay, so you can literally look up dictionary. There
it is.
Capital
T key, T value. Oh, it came up. I saw it. Just
there we go. There we go. Yeah. And so here's the buckets, and here's the entries, and the entries are like hash code, next value. And so you can already see it's actually not quite the same thing because how does this even work? This is way
well, if you
more
look at the keys, but if you look at the keys property, I was just referring to the fact that the keys property is not really going to give you the direct access to it.
No. Okay, so
further down, it's sort of like it's an iterator over
let me give
a class
you this
called key collection.
Let me give you this example because this one's way easier, and we've been looking at this code.
Yeah. Well, it makes me ask so many other questions, but
So sorted draw list actually has enumerating structs. So here's a struct front to back enumerable that implements IEnumerable, and this is like, all right, here's the 1 bit of storage for it. Here's the draw list. Sorry, that's the enumerable. Here's the 1 bit of storage for it. Here's the draw list. Here's the I, and here's the current. I don't know why there's an I and a current.
This is indexed into the drawing info table.
It's because I was kind of slack when I was writing this. I think they're basically the same thing. I just used the standard template for this thing rather than making it. But the point is that this is a struct. It's going to fetch us, it's move next. It's going to get us the current thingamajig, current drawing info, but it's not going to allocate anything. It's not going to do anything other than index into the thing we have.
Right.
So that's how these things work. What I was going to say about this, so this is like, I mean, it almost goes without saying because we've pretty much covered it, but it's like, this is the thing you access a bunch in a dictionary of like K value. It's like, and in a really simple dictionary, you're just going to be like key. That's the access pattern. If you put it in memory like this shape, here's one cache line, or it's probably more likely it's like here's actually if you're coding like this, here's like one cache line, here's our key, and here's like most of the value, because value is probably like a struct that's like blah.
Too long, yeah.
And so every time you check a key, it's like that. Whereas if you do it, instead of going that way, if you sort of go this way, it's like, all right, keys is an array and values is an array. Here's like a cache line. Let's find the key that we want. And now we'll take the one hit to load up that into a cache line.
Right, which is what you think you're doing, but aren't when you build these kind of things.
Yeah, so if you build these in sort of the naive way, you will hit this sort of memory problem, and your program will get like it was 20 cycles to access L2 was what I said, and hopefully I'm vaguely right, but like this is 20 times slower than it could be.
That's
which is a lot.
pretty amazing. Yeah.
Like if River City was 20 times slower, I don't think it would work.
No, plus we wouldn't be able to have the, running, like people were showing us, it's running on an XP machine.
Oh yeah.
With almost nothing installed on it, like with 90s or late 90s GPU, and it's like, cool. Runs fine.
So yeah, that's our little diversion into struct of array land. So that's really, I can't understate how important that concept is. I want to find like a few more examples. Like we didn't do it everywhere. Like actor is example, just like that's you've got an array of structs and the structs are actor and there's inheritance and it's all object oriented and it's got a state machine.
But I think there was a kind of a reason for that, because I think I remember you telling me about cache coherency during the development and how because we probably have to load the whole thing anyway. Like there's really there's no reason to think about it at that level, because we kind of need everything that's there. At that point, you have to have the rainbow because you're literally accessing the whole rainbow.
Well, yes and no. This is the painful bit. So first of all, there's the problem that actors like it's got inheritance and stuff. So it's like we need some way of dealing with that. But if you look at the interface for what actor does, is it all an actor? Is it some of it's on state machine? So already like we could possibly have the state machine in a separate array, for example. I don't think, actually maybe not. Okay, so but let's look at what the actor interface does. We build it, we set up the state machine. Okay, so we register physics. So there's a loop out at the top level of the game that's like go through every single actor in the tree and register physics on that actor.
Right.
And what this does is like, all right, get the actor's animation set height map. If it's not equal to null, add static physics of that. Otherwise, I guess do nothing.
Right. So you have a height map that use it to produce your static volume. If you don't, then leave it alone.
And you can imagine that we're grabbing out the animation set, the position, and the facing left, and that's it.
And yet we've had to load the whole thing because of the way it was
exactly. Yet we've had to load up the whole actor into the cache.
So it's like a whole new level of performance we could be getting here with. So
this is really tricky because this is one of the things you have to balance off this optimization against you have to balance off this optimization versus other things you could be optimizing, other things you could be doing. For example, like the whole actor class, I mean, you wrote all of the actors, and that was, I mean, fairly straightforward. It's like, I want to make a new kind of actor, let's inherit from actor and just set it up. And you can imagine how that would have become more difficult if it's like, well, actor is not just a single class. It's like this array and this array and this array and this array, and they all have to be kept in sync and so on.
Yeah, actor position info, actor physics info, actor connection data, actor. Yeah, there's a lot of stuff in there. I mean,
yeah.
There's the smoothing and the
render position, the smoothing, register shadows is another external loop, and so we could have saved
sorted.
Exactly, we could have saved a lot of probably a fair bit of processing time. But the other consideration is that we actually had a memory constraint for this game. What was it? We were 20 kilobytes.
Reach profile.
No. The network memory constraint. What was it? It was like 20 kilobytes or something.
I don't recall. I mean, you're referring to the startup memory pass during the network handshake, or what are you referring to?
I'm talking. Yeah, there's the startup memory to state transfer a snapshot across the network.
Yeah.
It was in the order of tens of kilobytes.
Yeah, that's right.
Which is.
It's like a very, very stern comment. Keep this super small.
Yeah,
exclamation.
That ended up growing a couple of times during development. What did I put?
A couple of many times. I think because it had like so many unlockable characters, and having to pass kind of like backpacks of all of those characters was
that one was a bit different because we actually had to transfer that one in many cases rather than just once on startup. Whereas the full game state was
Oh yeah,
could be
true.
smaller, could be
I think
bigger.
I think I was talking about the I think I meant to say like the characters that are coming into the game, but they have a lot more data in them than you don't like. Like money, their money storage is like in a whole integer.
Oh yes,
And there's like 4 or 5 shorts in there too for all of their RPG stats, rather than a pointer to go get those later. Like they're just all there.
yes. That was a fun thing to pack, but that was more of a networking thing than a performance thing for this.
Oh, okay.
But the point was that we knew that the game state would be limited to like, let's say 20 KB. In fact, it was a bit more in memory because the network does packing to get it down to this size. But it's like that's going to fit in L2, so we're never going to be like spending 200 cycles pulling in objects from like RAM to L2. So we're only going to take the hit from L2 to L1 when we're doing like something like an actor, bringing an actor into memory. If it, I mean, even if it, like there was a theory, and I'm not sure how well that theory held, that the entire game might fit in L1. Because I mean, 20 kilobytes, 32 kilobytes, there's pretty similar size. I don't think that does hold because we actually have to go off and grab a whole lot of data, like like the height maps, like the shadow layers, and so on. So I'm not sure that actually works. But still, so we're not. The point is, we're probably not going off to RAM because we've got 4 megabytes of L2.
Right. Whereas I mean, I can only guess that if I mean, I don't know. Unity's probably well optimized under the hood, but if we're gonna make a game in Unity, like we don't really get the real option of doing anything different, right? I mean, I guess that's a completely different problem because all the game objects are owned by that engine, so you don't have to think about it, but then you also don't get to think about it, so you don't get to arrange your game to be that performant. I'm curious what would happen if we ran it in Unity.
Yeah, well, I mean that's a whole different problem because like we would have had to write our own sorted drawing algorithm, for example, and we'd end up replacing huge bits of Unity.
Right. Fair enough.
But like this is the thing. It's like, okay, the draw sorting, that has to be nice and snappy, nice and fast. And so this one is like really heavily optimized, whereas the actors, this is actually more optimized for making it easy to develop, because like I don't know if have we ever done a count of how many actors are in the game? There's like a couple of hundred.
Yeah, I think there's more than that.
We have done it. We have done a count because I remember doing a count.
Yeah, I mean, there's at least far over 100,000 frames, which breaks down to, from a data point of view, I mean, thousands of frames per actor in terms of like their animation data, and then in terms of how many there are, yeah, there's definitely more than 100, probably more than 200.
I'm sure there must be more than 200 because I mean every crate, every box, every projectile, every weapon, every actor, every enemy.
And projectiles themselves are sometimes multiple actors. There's the projectiles, as it's coming out, there's a projectile when it converts to an explosion. And that explosion might have tracer shapes or, sparks or any kind of ground effect. And, absolutely. I don't know how many there are, but there's many. You probably do it live, but yeah, hundreds and hundreds. So yeah, when you want to, you definitely, this was quite helpful because it's not also that. I mean, we're not looking at the state machine part of that. Like underneath the actor, the state machine, and then there's
hundreds of states,
thousands. I think hundreds of states, at least dozens per actor.
I remember tweeting
each one. Yeah, every one of them has, the standard state for like, falling and climbing and ducking and jumping and punching and blocking and breaking the block and whatever. There's at least 40 or 50 sort of bog standard states, and then on top of that, you know, each character has like 15 moves, and those moves can be 6-7 states each because of, you know, wherever you are in transition, and then there's complex choreography of the attachments and so on. So absolutely, it would. I mean, you know, I know that I programmed at least 540 moves, unique moves. So that's at least 540 states that are devoted to nothing but combat. So I know that. So I know that. I know that at 3 in the morning on a particular day, I don't want to be worried about cache locality. I want to put the code in that does the thing, and then go, you know, put an X in a spreadsheet and go to the next one, because that's the grind of it. I mean, once you've gotten all the clever bits figured out, it's really just content, you know, wrangling. So yeah, absolutely. I mean, I think you probably could have done it in a way that hid it. In some areas at least, but I think that yeah, you're going to start to really worry about productivity concerns at that point.
Exactly. So like starting out, I mean, this is kind of the thing, is like you have to sort of, in fact, know a little bit up front what your requirements are. It's like, all right, I know that the game state has to be below 10 kilobytes or so.
And that's because of the rollback design, right? I mean, a lot of games don't have this restriction. But.
Exactly. And because I know that, then I know that's like, all right, the whole game state is going to fit into L1 in a pinch. So it's like, I don't need to optimize this particularly heavily. And you know, we'll spot optimize things where appropriate. And like, so for example, you can imagine, like you can imagine that this could be done a lot worse. Like this, where is it? This sorted drawer. Like, we could store this stuff on the actor. And then, so every time you have to sort through, you have to actually walk through every single actor, rather than it doing it in a sort of more intelligent way that just pulls the information it needs into a very well-packed array and then blasts through it when it's actually drawing things. So it is, in fact, in a sense, it is actually optimized in a SOA way where it counts. So yeah, it could have been worse. This particular bit of code, but
I mean, you could go all the way to the point where the actor's got everything that the fighting character does to the, you know, and just have a whole big. And
I mean, like say we started to actually have a performance problem. For example, like, okay, this is a virtual draw function. Almost every single actor is like current animation, current frame, draw context, get position, smooth, facing left. We could actually pull this out into a separate way. We could probably do something similar to the sorted draw list. We just have another, you know, drawing info might even get bigger. It's like, all right, here's how you draw all of the stuff in the sorted drawing list, just so you don't have to reload everything during the draw, for example. So we could shift the data around, and we could like be like, all right, here's the top level method we need to optimize. Here's a different one. Like, this one is already optimized in a sense because we're adding it to the sort list. And you know, we could optimize it more. Just, it depends what the profiling does. Like we, you know, there was a fair bit of profiling happened on this game to make sure that, you know, nothing was particularly slow.
That's right.
So yeah, that's we've kind of
yep.
we were doing some vectory stuff, but we had a little intermission there with the River City code. But hopefully that was worth the listening.
I think it was for me, just from the point of view of remembering to. It's almost like the, you know, the I hat J hat thing. You know, constantly remembering, hey, you're in a coordinate system. You don't get to choose. It's like encoding. You don't get to guess the encoding. You have to know what the encoding is.
Yes.
And that's like, you have to know what the axis is, or the coordinate space you're in is. And now with this, like, you also have to know where your data is and like
Exactly.
what you're trying to get. So I think it's super important. I think it's like a cornerstone thing. So I'm not too worried about having gone to doing that instead of maybe doing square versus circle, but we
Yep.
could do that on Wednesday.
I'm glad that rat hole was not too holy. All right, I think we're now slightly over time, so we're gonna have to wrap this one up, and we'll come back to doing this, but hopefully this will be nice and quick because it's basically the same. It's like, I'm wondering whether we can just copy this code. We probably can copy a fair bit of it. So
yeah, we're probably gonna copy it and then store it, and then basically switch the circle and rectangle ones to refer to that instead of doing their particular ones, right?
Yeah. So it should be nice and simple. So where's OBS? All right. Thanks for watching, YouTube. We